Hello, my name is Ruhe, and in this presentation I will talk about cone beam image quality improvement using a deep learning UNet model. I did this in collaboration with my supervisor Pascal Wiggers at Sursara, which is located at the Science Park in Amsterdam, and at the time I studied at the University of Applied Sciences in Amsterdam. So first the content page. I will briefly describe the assignment I got from Sursara, then some information about the cone beam CT scanner, following up with, of course, the UNet model, what layers it uses, and the data/model parallelism. And in the end, of course, the results of the cone beam image improvement. So the assignment. Sursara works together with the Netherlands Cancer Institute, which is a dedicated cancer center and maintains an important role as national and international center of scientific and clinical expertise development and training. Sursara works together with the Netherlands Cancer Institute because they make use of a cone beam CT scanner. And the typical thing about a cone beam CT scanner is that it uses less radiation, but because of this, the quality of the CT image also goes down. And the assignment I got from Sursara was that I should try and increase this cone beam image to a regular CT quality image using a UNet model. So the cone beam CT. A cone beam CT has a cone ray structure, which can be seen in the bottom left here. It has a cone beams. It has a structure like this because this way with each image it makes, it covers a larger surface of the head, and this way it needs to make less images, resulting in less radiation for the patient. But because it covers a larger surface, the amount of radiation that actually receives the detector in the end might fall away in some parts, and this way more general noise in the image will be created, and typically black spots will appear in the image, and compared to a regular CT scanner, it's lower. The image quality will be lower, but the amount of radiation it will use is less. So I try to remove this noise using a UNet model. Typically a UNet model is a fully conventional network, mainly used for image segmentation, but in this case I tried to use it for image quality improvement. And the typical layers or the architecture of a UNet model is it makes use of convolutional 3D layers, max pooling layers, concatenation layers, and those are combined with upsampling layers, or also called convolutional 3D transpose layers. Another thing to note about the UNet model is that it's invariant to image size, so each image size can be fed into it as input. This is typically what the 3D UNet model looks like, where on the top left it gets an input of an RGB value, for example. And in this case, it could be a dimensionality of 512 by 512 pixels. And then the first step it's going to do is do some convolution operations on it. So it's going to increase the amount of feature maps to 32 and then to 64. But of course, the output quality of those feature maps will be very, very poor because the filter in the beginning is completely random, and this way the output will be completely random. But this filter will adjust itself after each iteration, and after a day of learning it will be improved significantly. So after two convolutions, it does a max pool. This has to be done because otherwise you're gonna get problems with the memory of your GPU, and the max pool basically pulls out the highest valuable data of your previous feature map, and also decrease your dimensionality. So from 512 we're going down to 256. And then it's going to repeat this process over and over. until we have a lot of feature maps with a low dimensionality, a lot of high resolution feature maps. And in the bottleneck at the bottom, it's going to start doing transpose convolutions with the yellow arrow, and it will build up this dimensionality again. And with each layer, it's going to concatenate with the green arrow with previous high resolution feature maps. And this is the main point the UNet model does. Because after this concatenation, it is going to do this concatenation with each layer while reducing the amount of feature maps with the convolution layers, and also building up dimensionality again with the upsampling layers. And the main purpose of the concatenation is that it's going to concatenate high resolution feature maps from the previous layers with the upsampled layers on the same level. And those high resolution feature maps will increase the chance of pattern learning the model might find, and in the end also increase the image quality output. So during my research, I used data parallelism with the framework HODLVOD, and with this framework, the model is placed on multiple GPUs. For this case, I used 4 Titan RTXs, and it increased my training speed significantly, actually 4 times as fast. I did this because now I could just see my results much faster, and the results I got much faster. But if you're gonna use high dimensions of images, because there are cone beam CT scans out there that can create, for example, 1024 by 1024 image sizes, the amount of parameters that will be created are enormous, and no GPU can handle this amount of memory. So the model needs to be split up over multiple GPUs. And I tried to do this with TensorFlow Mesh, but sadly I did not succeed, but I know this is possible. And this needs to be done in order to have higher resolution images if you want to use this, because higher dimensionality on images will increase the amount of feature maps and then also increase your output accuracy. Yeah. So then, of course, the results. I have to note that this is not a real cone beam image. This is because I could not get the real data set from the Netherlands Cancer Institute due to the coronavirus. So I tried to replicate them as much as possible myself by adding general noise to the input image and creating those black spots, which is typically a problem with cone beam images, which can be seen in the middle image. Then on the left side you have the input image, and on the right side the reconstructed image based on the noisy image in the middle. And you can see it does a very good job in replicating it, but the smaller details like the white matter in the middle of the lung or on the outside is a little poorer than the input image. But it has been training for 2 days in this example, and the loss was still going down. So maybe after 3 or 4 days, it would have increased a little more. So in general, the UNet model does a very good job at trying to reconstruct those cone beam images to regular CT images. And this was it. Thank you for listening.